Hi, in this video we are going to visit example 5 and try to interpret it in a different way. Okay, so first let us remember what we did in example 5. In fact, that example is related to the calculation of the Fourier series of an output signal of a linear time invariant system corresponding to a periodic input, and the periodic input is chosen as the impulse train. So we have our linear time invariant system with input x of t and output y of t, and the impulse response of the linear time invariant system is h of t, and h of t is given as the pulse. So h of t is just equal to 1 from 0 to t0, and it is 0 outside this interval. Okay, now x of t is chosen as the impulse train, and from minus infinity to plus infinity, delta of t minus m t0. So we have the signal x of t given as an impulse train, which is of course periodic with period capital T0. So we have impulses at 0, T0, 2T0, etc. And here we have minus T0 and the negative part of the horizontal axis. And each impulse has strength equal to 1. Okay, the area under the impulse, in other words. Okay, so the Fourier series of x of t is ak e to j k omega 0 t, k running from minus infinity to plus infinity, and k is, omega 0 is of course related to t0 by 2 pi over t0 by means of this expression. And ak's are all equal to 1 over t0. We have calculated this in example 5, in the previous example. Okay, the output corresponding to this input y of t is again a periodic signal with Fourier coefficients bk, k running from minus infinity to plus infinity. So bk was calculated as 1 over t0, t0 e to minus jk omega 0 t0 over 2 sinc k t0 small t0 divided by capital T0. So this is bk. And what was the approach in obtaining bk? In fact, this first term here is ak, and the second term is, remember, obtained by means of the system action of the LTI system when the input is chosen as the complex exponential signal e to jk omega 0 t. And we can show this by the notation capital H of k omega 0. And remember, this is just the convolution of e to jk omega 0 t in fact, it's obtained from the convolution of, okay, let me write it in this way. This is the complex constant obtained from the fact that the complex exponential signal is an eigenfunction of the LTI system. Therefore, the system action reduces to a multiplication by a complex constant. So this is the complex constant obtained by using the fact that e to j k omega 0 t is an eigenfunction of the LTI system. Okay, in other words, here maybe we can show it in the following form. This is our LTI system with impulse response h of t. So when the input is e to j k omega 0 t, the output is h of k omega 0 e to j k omega 0 t. So essentially the signal is unchanged in form, only multiplied by a constant, which is a complex constant, meaning that the magnitude is changed and there is a phase term coming from the argument of the complex constant. Okay, this is in fact what we have done in the previous example. Now we are going to look at this problem from a different viewpoint. Okay, so we will continue to discuss the problem, but by means of a different argument. Okay, now let us look at the problem as follows. Now our x of t is in fact the impulse train, and from minus infinity to plus infinity, delta of t minus m t0. So we have the impulse train as the input of our system, impulse train, and the impulse response h of t is the pulse, which is equal to 1 from 0 to t0, and it is 0 elsewhere. Now we know that by the definition of the impulse response, if our input is an impulse, this is our LTI system, the output is the impulse response, h of t. Now we know that the system is linear and time invariant. Now we are going to make use of that fact. But first of all, in order to simplify the problem a little bit, we assume that t0 is less than capital T0. So let us assume that t0 is less than capital T0. So by time invariance, by the fact that the system is time invariant, delta of t minus mt0 for any integer m, positive or negative, the corresponding output is h of t minus mt0 for any integer m. Okay? So, since we know that delta of t gives us the output h of t, the shifted impulse, shifted by the amount m capital T0, will give the impulse response, which is also shifted by the same amount, by time invariance. Now, in x of t, we have these terms as individual terms. Now, we have the superposition of these terms, so by linearity, the superposition of these impulses applied as the input signal will give us the system action will give us the output m from minus infinity to plus infinity, h of t minus m t0. But we know that this is our input, x of t. So therefore, this will be the corresponding output, y of t. Okay? So y of t is obtained in this way. So if we look at the graphs, x of t is the impulse train minus t0, 0, t0, 2 t0, etc. And corresponding to this x of t, the output will be y of t will be now composed of these periodic repetition of these pulses, rectangular pulses. Okay, so this is this pulse starts from 0, this one from t0, this is from 2t0 and minus t0, etc. Okay, and the magnitude is 1. Now, we know that y of t has the Fourier series coefficients bk And remember that we have obtained this by means of using the system action and the fact that the complex exponential signals are eigenfunctions of the LTI system. But if we look at BK once more, we will recognize this as the Fourier series coefficients of this rectangular pulse train. So we have T0 over capital T0 e to minus jk omega 0 T0 over 2 sinc k T0 over T0. Okay. Now, we recognize the term sinc term and this constant T0 divided by capital T0 as the coefficients of the Fourier series coefficients of the rectangular pulse train, but where the rectangular pulse is as duration T0, but it is located in the interval from minus T0 over 2 to T0 over 2. So here we have a shift by T0 over 2. So this is corresponding to the time shift corresponding to the time shift by an amount T0 over 2. And the remaining terms we recognize those remaining terms as the Fourier series coefficients of the rectangular pulse. So this is a different interpretation. By the way, why did we choose T0 less than capital T0? Well, in fact, there is no need for such a restriction, but under this choice, the pulses will not overlap when we evaluate y of t. The result is still correct when T0 is chosen arbitrarily, but there we will have overlaps and we will end up with a periodic function which is not simple to draw in graphical form. So in order to have a simple graphical interpretation, I have chosen T0 less than capital T0, although there is no such necessity. Now finally, I would like to underline an important point. Remember that we obtain periodic output signals when the input signal is a periodic signal in LTI systems when the system is stable. Now, in this example, the system is, of course, stable because the condition for stability is that h of t must be absolutely integrable. Here, h of t is just a finite duration pulse. It is one from 0 to t0, and of course, it is integrable. So, finally, as a remark, note that we have no problem with stability. Our LTI system is stable since from minus infinity to plus infinity, the integral of the magnitude of the impulse response is finite. And therefore, our analysis is valid. Remember, this analysis is not valid for systems which are not stable. In that case, in the convolution integral, we have the improper integral there is divergent, and we have a serious problem. If our system is stable and linear and time invariant, then a periodic signal at the input will always yield a periodic signal at the output with the same period. Okay, so thanks for watching.